All right, moving on to example number 2. Again, we're given the equilibrium constant for a particular reaction, and we're told the initial concentration of the reactants, and we need to figure out the equilibrium concentrations for each of the gases when it's at equilibrium. So again, as usual, we're going to set up our ICE table to begin with. Again, we're looking at our initial concentrations, we're looking at our change, and we're looking at our equilibrium. To start off with, I'm told that we have 0.50 moles per liter of N2. We have 0.25 moles per liter of O2, and we have 0 NO. Taking a look at our coefficients, I can predict what the change might be. So I know that this is a coefficient of 1, this is a coefficient of 1, and this is a coefficient of 2. So because these are reactants with existing concentrations, they are going to decrease by X. And because NO has an initial concentration of 0 and the coefficient of 2, we know that it's going to increase by 2X. So using these, I can figure out an expression for the equilibrium concentration for each of these gases. I'm going to write this at the bottom just to give me a little bit more space. For N2, I have 0.5 minus X. For O2, just so that we're keeping things separate, I'm going to change my color. I have 0.25 minus X. And for NO, I have 2X. Okay, so I've got three different expressions for the concentration for each of these entities. Now I'm going to do exactly what we did in that previous question and write an expression for the equilibrium constant. K is equal to, and I'm going to write the concentration of our product raised to its coefficient, which is 2, divided by, that looks really weird, divided by, divided by the concentration of the reactants raised to the exponent, which is 1. There we go. So this is my general formula. Let me plug in my expressions here. NO2, I know that the concentration of that is 2x squared. So all of 2x is going to be squared. That's going to give me 4x squared divided by 0.5 minus x and 0.25 minus x. And my K value given in the question is 6.8 times 10 to the power of negative 8. Now, this question is different from any of the ones that we've seen so far because we can do a test on this to make our calculations a lot simpler. So this is something that you should watch out for whenever we're doing equilibrium concentrations. So something that you should always do, a test that you can always do, is I want you to compare your initial concentrations of whatever entities you're given the concentration of by the K value if it's given. So in this case, let's compare the concentration of N2 to the K value. And when I say compare, I just mean we're just going to divide those two together. So let's do our little comparison test. So the whole point of this is that if we see that this is what it is going to be, we can make an assumption that that will make our calculations a lot easier. So let's check for N2, which is what we're given first. If we are making this test, we have to take the initial concentration, which is 0.50, and divide by our K value, 6.8 times 10 to the power of negative 8. Now, if this expression, when I divide these two values together, if that is greater than or equal to 500, then I can do a certain assumption. What I can do is I can remove this minus x part. What we're essentially doing here is we're saying that this x that's going to happen, this change that's going to take place, is so minuscule that we can disregard it. So we are going to get rid of this minus x part. only because when I divided 0.5 divided by 6.8 times 10 to the power of negative 8, I get a number that's way bigger than 500. If it's equal to or bigger than 500, I can make that assumption. Now let's do that test for O2. So for O2, if I take 0.25 divided by 6.8 times 10 to the power of negative 8, is it greater than or equal to 500? It is. It is, again, a really, really big number. And because it is greater than 500, I'm going to get rid of this minus x part, right? If I had that, I could do my calculation, but as you saw in the previous question, that involves the quadratic equation, and it's a lot more work, and this will really simplify your answer. So if I go along with my assumptions, I'm going to make my calculations based off of that, and let's see what the answer ends up being. So I have 6.8 times 10 to the power of negative 8 is equal to 4x squared times 0.5 times 0.25. Again, I got rid of that minus x for each of those concentrations only because when I did that test and I saw that it was greater than 500. So if that works out, you should go for it because it'll save you so much time on your assessment. So 8.5 times 10 to the power of negative 9 is equal to 4x squared. So what I ended up doing is I multiplied these two values together and I took it over to the other side and multiplied that by it. Now, in order to solve for x squared, I'm going to divide both of these side by 4, which would give me 2.125 times 10 to the power of negative 9. Solving for x, 4.6 times 10 to the power of negative 5. That would be the value of x. Now, I want you to do the test if you are curious and if you have the time. If you do this entire calculation without making this assumption, the answer that you get for x is going to be exactly the same, right? So if you didn't cross out the minus x in both of these and you solve for x, the x that you're going to get is going to be the exact same. You can do that by trying it out that way, right? So maybe grab out a line sheet of paper and try it out to see if that works out. You're going to see that the answer for x is going to be the same. And that is going to really show you that if you can do this test to see if that assumption can be made, you can make it, and that way you'll save a lot of time. So using this, I can again solve for what the question asks, which is the equilibrium concentration of each gas. So for NO, so the concentration of NO is going to be 2x, which is 2 times 4.6 times 10 to the power of negative 5. And the concentration of N2 is 0.5 minus x. So N2 is equal to 0.5 minus x. And the concentration of O2 is going to be 0.25 minus x. So when I plug these into my calculator, the numbers that I'm going to end up getting are going to be so for the concentration of NO, I will get 9.2 times 10 to the power of negative 5, again, moles per liter. For the next one, 0.5 minus 4.6 times 10 to the power of negative 5, it'll give me 0.499. So I'm going to do 0.5 moles per liter. 0.25 minus 4.6 times 10 to the power of negative 5 is 0.25 moles per liter.